Alrighty. Hello, everyone, and welcome to today's webinar, What's So Phenomenal About Phenomena. We're so glad you took time out of your very busy day to join us today. My name is Heath Williams. I'm the marketing manager for Amplify Science, and I'm joined today by Rebecca Abbott. She's the professional learning lead at the Learning Design Group at UC Berkeley's Lawrence Hall of Science. You've probably heard of phenomena-based instruction. It's probably why you're here today. And Rebecca is going to walk us through what this actually means and how it's embodied in an NGSS design curriculum. Before I hand it over to Rebecca, though, a couple of quick housekeeping notes. You're going to be on mute for the duration of this webinar, but we do want to hear from you. You'll notice a Q&A button on the bottom of your webinar screen. Drop any questions you have there as we go, and we'll be sure to leave some time at the end of the session for a Q&A. Rebecca's also going to be asking for some participation throughout the webinar. You can drop your responses at those moments in the Q&A tab as well for us to read out. This webinar is also being recorded. You'll receive a link in your email tomorrow with a link to the recording to watch on demand or share with colleagues who may not have been able to make it today. So be on the lookout for that tomorrow. And that does it for logistics. So with that, let's get started. I'm going to hand it over to Rebecca.
Great. Okay, thanks, Heath. And thank you, everyone, for joining. There's been so much talk about phenomena in the next generation science standards, and I'm happy to be here today to dig in with you and about what that means. So the focus of today's presentation will be to showcase the approach that we've developed to phenomenon-based teaching and learning. And this approach is part of Amplify Science. So I work here at the Lawrence Hall of Science. My role is as professional learning lead. And we've been in deep collaboration since the beginning of this project with Amplify to publish and bring the program to all of the schools. So while I'll be using examples from Amplify Science, the goal of this session is to really illustrate what a phenomenon-based approach to teaching and learning looks like, not necessarily to focus on the curriculum itself. So what we're going to do is dive in to spend some time thinking about a phenomenon-based approach to teaching and learning, as the title says. We'll start off with what this means, then move on to why this is a powerful approach, and then share an exemplar of how it can look in a classroom. Now, this session was designed originally as a hands-on workshop in person with actual materials. So we can't do that today. I don't know if you have ice and cups and all of that in front of you, but I do want to stop every so often to ask you questions, and I'm hoping you can use the questions features to chime in with your responses. So there are some activities I'll just talk you through and others I'll have you respond to. And then later in the presentation, I'm going to project a simulation. And I'm hoping it will be possible for you to make some firsthand observations and gather evidence in that digital format, even though you won't be actually driving the simulation itself. Okay, so that's the plan for our morning here, or our afternoon. So let's start with this. What are scientific phenomena? Phenomena are observable events that occur in the universe and that we can use our science knowledge to explain or predict. And phenomena, of course, is plural for phenomenon. Let's thinking about how science topics and science phenomena are different. And this is somewhere where I do want you to chat in your responses. So I want you to take a moment or two to think about the difference between a science topic and a science phenomenon. You can see on your screen, we've got things like the water cycle, all about sea turtles, energy and matter as topics, and a potentially equivalent phenomenon. So go ahead and chat your ideas about how are topics and phenomena different. And I'll watch the Q&A button to see if your answers roll in. All right, I've got a couple folks saying here that, okay, the topics are more like a right, wrong type of thing. People say topics are things that they can envision, something that would be in a textbook, like they can picture the diagram of a water cycle and memorizing the parts of a water cycle. Someone's mentioning that phenomena is more specific, meaning that it's about a certain place, or a certain, in this case, certain place or certain habitats. And the topics and the phenomena are more real world. They invite curiosity. We hear a lot of people saying that, and that the topics are potentially less motivating, not a lot of connection to those. Okay, so great. So hopefully you had some of those same responses when you saw these two lists. So I'm going to go now to a similar slide where it's interesting to think about how units of instruction would be different, depending on if it's organized around a science topic, like on the left-hand side of your screen, and on the top or around a scientific phenomenon. The topics lend themselves to facts, as we mentioned on the last slide, memorizing or having discrete knowledge related to these topics. Phenomena, on the other hand, lend themselves to why and how and what caused kinds of questions, the kinds of questions that scientists ask. So while phenomena are described in statements, one can easily turn the statement into a question, such as what I have here. And we've got one more comment too, that phenomena explains a natural occurrence, which is what we see in these cases. These are things that are naturally happening in the world around us, and that they discuss, and while a topic is a subject that discusses phenomena, and I agree with that there's there's relationship between the topic, there's a subject that you might study about or think about while figuring out ideas about a phenomenon. So thanks for that comment. So what we might see then is that when we're talking about the NGSS, call the main phenomena that guides a unit or instructional sequence the anchoring or anchor phenomenon. And it's called this because the entire unit is about figuring out the phenomena. An anchor phenomena invites asking students to ask why or how does something work. It needs to be rich and complex enough that it can motivate the learning and the investigations for an entire instructional unit, however long that lasts. And an anchoring phenomenon, like someone mentioned in the comments, is specific to one event or location. It's not just generally, how does something work out there in the universe? So for instance, we asked what caused the storms in Galetown to become more severe, not just what causes storms to be severe in general. Okay, so that's a little bit about what the differences are between topic-based and phenomenon-based. I'd like for you to think for a moment now, and I will have you chat in your responses once again. Why? Why are we making a shift to a phenomenon-based approach? What are the advantages? What does it offer our students and our teachers in terms of teaching and learning? So go ahead and chat in your responses there as well. All right, we've got some answers. For example, if we want students to engage in learning about the natural world, this gives them opportunities to construct those ideas. There's a comment too about critical thinking skills that are related to real world connections. It makes the topics of science more real to our students. Yeah, really nice comments. It's okay if I saw someone commented they can't see the comments, that's okay, I'm just reading them out loud. And the other one is that it connects a study of science to a real life event. So yeah, I think all of these comments about these being real life and these being something that engages the students are exactly right. These are huge reasons why the fact that it is authentic to science. And scientists don't wonder about topics. Scientists in the field wonder about phenomena. We think about what we wonder about in our natural world, and what scientists are studying right now, they're about phenomena. And science is about figuring things out. You can't figure out a topic. You can figure out a phenomenon. It's through figuring out phenomena that scientists become versed in a topic area. If we want students to engage in learning about the natural world as scientists, then we want to afford them the opportunities to construct their knowledge in these ways that scientists do. And another thing that we hear from a lot of people is this idea that focusing on phenomena leads to this more authentic interdisciplinary approach, where you're not just studying about the science topic itself, but you're reading and you're talking about life science, physical science, earth science, math, other ideas within the context of a phenomenon. And so the focusing on instruction on phenomena really changes our focus. When we focus instruction on phenomena, the students are motivated to explain. What it does is it shifts the focus from just learning about to figuring out. This is one of the most significant shifts of NGSS, this move that it helps us achieve, which is moving from learning about to figuring out. And most of you are familiar with the fact that NGSS has what's called three-dimensional teaching and learning. And we're really not sure that it's possible to do three-dimensional learning without a phenomena to figure out. 3D learning is a structure that helps support making the shift that moves students from learning about to figuring out. The 3D structure, most of you know, is about having students use science and engineering practices and applying cross-cutting concepts to figure out core ideas. And science is about figuring things out. You can figure out what caused a phenomena, and it's through figuring out what caused a phenomena that scientists become versed. And they do this using all 3 dimensions. Okay, so we spent a little time on what are phenomena and why might we do them, which all of you contributed, saying it was more authentic to the work that scientists do, having students figure out. So now we're going to jump into how. How does phenomenon-based teaching and learning look in the classroom? To do that, I'm going to use an example from one of our 5th grade units. We've got a kindergarten through 8th grade set of units that cover 100% of the NGSS. The one I chose to just showcase for you today is one of our 5th grade units called The Earth System, Investigating Water Shortages. And so what I'm going to showcase in this unit will help you gain insight into all Amplify Science units, grades K to 8, how we designed units of instruction to guide students to do this figuring out of a phenomenon. Okay, so we'll jump in. In all of our units, students take on the role of either a scientist or an engineer. And in this case, students are water resource engineers. And what happens is that they're tasked with figuring out what's happening on this particular island. Specifically, they need to know why one side of this island that you can see on your screen is experiencing water shortages and the other is not. Now, Ferris Island may be a fictional island, but this is based on real world location. So this is something I've experienced in my life, and of course we would make connections to kids if they've ever seen a place that had more rain and one that had less. So just a reminder, like I said earlier, this is the anchoring phenomenon, or the main phenomenon that covers the whole unit. It's something that sustains the learning over 26 lessons, and the anchor phenomenon has to do with the fact that while one side of the island, East Ferris is having a water shortage, West Ferris is not. The question they're trying to answer is why? Why is East Ferris experiencing this water shortage? This is, again, the question form of the actual phenomenon. We break our units into learning sequences called chapters. This, on your screen, you can see this shows the 5 chapters of this 26 lesson unit. You can see the larger question about why is East Ferris experiencing a water shortage is broken down into 5 smaller questions. And we, of course, let students know that when scientists tackle big questions, they break larger questions into smaller questions. We're going to dive into just a little bit of the beginning of this unit, just so you see an example of how this works. Chapter 1 is all about defining the problem, where students are coming to really understand what it is they're trying to figure out. And then we'll dip into chapter 2 as well, this first part of actually figuring out the problem. And hopefully this will provide a picture of not just what phenomenon-based instruction can look like, but what it's like to have students figure out the phenomenon. And you may be doing some of the figuring out with me. So the chapter 1 question focuses students on further defining the problem. Those of you savvy with NGSS know that this is part of science and engineering practice number 1, asking questions and defining problems. Namely, we're in this chapter, why is East Ferris running out of water? We have to figure this out. Why is this happening? What is the problem exactly? It's a pretty short little sequence. There's only 2 lessons dedicated to defining the problem, but I want to talk you through what students do in that short sequence. So what do we mean when they're defining the problem? What they have to do is look at what we know about water shortages. And it starts with thinking about all the water on Earth, which students explore with inflatable globes. And then they get a book, and if you can see me, the book is called Water Encyclopedia. What they do is they look in this book that has reference of things like, where is all the water on Earth? And so if you're taking a look at my screen here, they get some support and some practice reading graphs to figure out where is all the water on Earth? What does this graph show? And if they take a look at this graph, they start to notice things and talk to each other about, oh, I see, most of the water in Earth is in salt water, in the ocean. And salt water is unusable for most human purposes. And if you take a look at that graph, there's very little water that is fresh. So this helps dispel one preconception that students have. What do you mean there's a water shortage? It's an island, it's surrounded by water. So clearly there's a difference between fresh water and salt water that we need to help us define the problem. And then we take a look, okay, where is this fresh water on Earth? How do we even get fresh water? Students are asked, well, what does this graph show? They would respond and talk to each other and talk about freshwater is mostly in glaciers and underground and groundwater. A very small amount is available for human use. We start to introduce different concepts to these fifth graders about the hydrosphere. And this idea of groundwater, we know from our research, is not something that students all have a very sophisticated understanding about. So in this particular context, we help define it. We take a few minutes to explain that groundwater is not like a giant underground lake. It might seem like there's big areas underground that are filled with water, like reservoirs that they have in their head. That's not usually the case. Even though the ground and the rocks below us seem solid, there are tiny cracks in the rock and spaces between rock that water can seep into. When you add up all the water in those tiny spaces, it amounts to a lot of the fresh water on Earth. So now we've got a hydrosphere and a geosphere connection, and we make those explicit to kids. Okay, so I want everyone who's on this webinar, there's about 25 of you, to take a look at the rainfall data we've got. Students are told that the mayor of East Ferris sent us over some data, because remember, we're the water resource engineers, on the amount of rain that each city has gotten over time. So as you're looking at it, what do you think this data show? You can go ahead and chat your response in the Q&A button. What are you noticing is happening in East Ferris compared to West Ferris? Okay, so as people are analyzing this data, I'm waiting for a couple comments to come in. So drastic difference in rainfall, and West Ferris is receiving a lot more rain than East Ferris. And the question is, you know, that we start to talk about with kids, okay, that's great that you can analyze that data, but is this evidence of a drought? What would it look like if there was a drought? And you can see here that there really is no drought, that there's consistently, that there is increased rainfall in some years, but there's never a time when it's gone lower, you know, sort of dropped lower than sort of a normal range. And they both align. That's another thing to notice, that both West and East Ferris kind of go up together and then go down together too. Okay, great. Thank you very much for those comments. Okay, so the question is, if there's no drought or it stops raining, which I know we here in California are experiencing, then why is there less water? So let's take a look here at what else is happening. East Ferris, we look at this population graph. So they go on to synthesize this information and also notice that the population on the island is increasing. And we ask students, well, why would that matter for water usage? The bottom line is that East Ferris is using more water than it's actually collecting. Because it rains more in West Ferris, they don't have that same experience of a water shortage that East Ferris would experience with this population increase. So again, this is sort of all in service of defining the problem. Why is there a water shortage? And it comes down to where the water is, how many people are there, and here we are able to synthesize why is there a water shortage. Which leads us to more questions. Well, so we've defined the problem. We figured out in chapter 1 that there's more rain. It's more rainy in West Ferris, but why? Why is it rainier in West Ferris than East Ferris? Why does that happen? They're on the same island. Doesn't make sense. Let's find out. So just like we broke the big unit question into smaller questions, here we are now breaking a second question, a chapter question, into smaller questions, which once we figure out will help us answer that chapter question. We call these investigation questions, and it's part of figuring out why there's more rain over West Ferris than East Ferris. And you can see the 3 questions: how do drops of water form, how do raindrops form, and where does this water vapor in the air come from? Now, while these 3 questions are a roadmap for instruction that the teachers might know, we do not show all these investigation questions to the students at once. This would give away some of the information, and we really want the students to be doing the figuring out. So we guide them at the beginning of chapter 2 as they're asking all these questions. We introduce one of the questions to students like, well, okay, so if we know it's because of water form, more rain, well, how do drops of water form? So students do this figuring out through a combination of hands-on, so the doing, lots and lots of student-to-student talking, and plenty of reading. So I'm going to talk you through how that happens. This will be the point in the hands-on. If I was face-to-face with you right now, I'd have you start to do some investigating yourself. So what we would have done is the teacher would challenge students to make drops of water appear on the outside of a cup of water. So please feel free to do this later on today. Try to create this phenomenon using a variety of materials. You can use cups and ice and water, and lots of people like to try to use a thermometer and try out some salt. You pay attention to what's happening and you observe closely. What students figure out from all of these observations and experimentation is that water drops form on a cup when the cup is cold. And so that's fine. We found a phenomenon. We observed something and we noticed something. This is something that's slightly smaller than the anchor phenomenon. Water drops formed on the outside of a cup of ice water. So what evidence can we find to answer this question of whether drops of water come from the water inside the cup, or do the drops of water come from the air outside of the cup? They have lots of ideas. Students can provide as much agency in this investigation as the teacher would like to choose. What they do is they find a couple of things. They observe a very cold empty cup from the freezer. As it's brought to room temperature, we see that the water drops still form on the outside of the cup, even though it had no water in it. So does it come from inside the cup? I'm not sure. And then we try another investigation where we talk about, oh, well, what about some Ziploc bags? We compare the same cups inside a bag that's Ziplocked with no air in it, and a cup of water that's cold ice water that's on the desk with no Ziploc around it. And we can figure out that the water drops seem to come from somewhere outside of that glass, because more water drops form on the cup that was not in the bag. So they gather this evidence through some hands-on investigation. But what's in the air that becomes water on the surface of a cold cup? To figure this out, students search for evidence, and back to this reference book, is they search for evidence in the Water Encyclopedia, and they take a close look at what air is composed of, that there's a place that surrounds the Earth called the atmosphere, another part of the Earth system. And they look at the composition of the air in the atmosphere. They notice there's something called water vapor in the atmosphere. They read that water vapor is water in the form of an invisible gas. There's water vapor, which is water in gas form in the air. And so just in sum, this is to review where we've been so far, and this is just over a couple of lessons. We know water drops form on a cup. So when the cup is cold, the water drops will form. We also know through some more experimentation that water drops don't come from the water inside the cup. They seem to come from the air. And then we've just figured out there's water vapor in the air. And that has us thinking that the water drops that form on a cup come from the air around the cup. So with all of these sources of evidence, we can, to respond to the investigation question, how do drops of water form? We're thinking, you can see what we call a key concept at the bottom. The drops of water can form when enough water vapor, it gets cold enough and condenses into liquid water. Okay, so I just talked you through our first investigation question, which always brings up, remember, we have more questions to ask. So this doesn't, how water drops form, we still have more questions. Well, why are we talking about more rain over West Ferris? What about, we know how regular water forms. What about raindrops? Now, in order to solve this one, well, let me actually pause for a moment here just to show you the structure of where we're headed. These investigation questions do help students what are called investigative phenomena. I already mentioned that. We have the anchor phenomena, and then in a smaller way, we have investigative phenomena. Things that we see every day, like drops of water forming in front of us on our cups, raindrops forming that we see every day. These are what we call investigative phenomena, and what we do is we ask questions called investigative questions. So what we do in a structured curriculum like this is we start off with an anchor phenomena. We investigate parts of that anchor phenomena when what are called investigative phenomena. And then students go forth and gather evidence from different sources, and that leads to the construction of new science ideas. In this case, it was, where did that water come from? These new science ideas in turn help students start to make sense of the anchor phenomena. And here's what it looked like in that first activity sequence that I just described to you. We were motivated by the anchor phenomena of East Ferris's water shortage to wonder why drops of water formed. And then we took on that smaller phenomena, gathered evidence from our hands-on tests and the book to figure out, well, why drops of water form. And we reached a conclusion about what can cause drops of water to form. So, but then, like I mentioned, we're not quite done figuring out this water shortage thing. So we would continue that cycle. New science ideas lead you to another investigative phenomenon. Each one gives rise to asking a question, leading students to gather more sources of evidence, that in turn help them construct new science ideas that eventually, little by little, get them closer and closer to figuring out the anchor phenomena. And that's what we mean when we say that these anchor phenomena can sustain the learning over a full unit. So again, where we are, we're trying to figure out why there's water shortage. So we work to understand how water drops form. And so let's work now to see how do the actual raindrops form. This prompts the next investigative phenomena. Now this one is a little harder to view in our classroom setting. We can't make raindrops form. So what we would do is we go to a computer simulation. We investigate how water forms. So this is where we describe that we'd use a simulation, and we describe that a sim is a model. A model is something scientists and engineers make to answer questions about the real world. So I've just got a screenshot of it here, and I'm going to go to the actual sim itself by just clicking over to a new window. So in all of our units, we have starting in grade 2, we have simulations and digital tools. One of the types of digital tools we have is a simulation. And so and what students do, especially in 4th and 5th grade, is we often have them pair up and make sure that they are engaging in a simulation activity with a partner so they can talk about it. I'm going to go ahead and demonstrate it though, not letting you play with it right now, but normally students would be the ones driving the simulation. So I'm going to go ahead and press play. You can see I have some features here on my right-hand corner of my screen. So when I press play, nothing's going to happen right away, but just wait a moment and observe and watch what's happening. And feel free to, if you're getting excited about what you're seeing, you can chat your responses or your observations in the chat button. All right, so I see some people saying, yep, I see some clouds, they are going up, I see some rain coming down, etc. So this is a typical thing that we might see when it starts to rain. Okay, I'm gonna press this reset button in the right-hand corner and reset the landscape, and it's gonna start immediately, but this time I'm actually gonna turn on the water molecules. So now I have a view of what's happening, and the same kind of thing is happening. And I'm getting a nice comment from one of our viewers here who's saying that's cool. And then she also said literally. So yeah, literally, we're noticing things get colder. That's a good observation. You're noticing the temperature graph on the side. So now we're seeing molecules happening. And it's very fun to watch. And so what the students start to notice is there's a movement of red molecules and the other molecules. So what and you can see in the right-hand corner of my screen, where there's a key about what's liquid and what's vapor, which of course they've had some experience with. The other thing that is on this simulation in my left-hand corner is an analyze button. You can see that sort of pulsing. It wants me to click on it. So I will click on that analyze feature. What this allows the students to do is take a more careful look at their simulation run. So I'm going to rewind it, and you can see it just kind of goes back in time to the beginning. So if I restart it, what I can do is rewatch what's happening. I'm just moving my scrubber forward, or I could just press the play button. But what I want to do is something was interesting to me, and as students, they would do this too, is, oh, there's this moment that's happening, that the water turns from, it seems from vapor, I'm going back and forth now, from vapor to liquid water. So you can actually click on some of these molecules and trace its path. So I'll just watch that one molecule go up. And, oh, it's still highlighted, but now it's not red anymore. It's blue. It's turned into a liquid molecule. So I can actually go back and I can take my atmosphere window and zoom and drag. And this gives us an opportunity to see what's happening in a zoomed in way in this little window here. So if I press play again, I want to kind of follow that to see what's happening. I'm going to keep following it, see if I can trace its little path. I'm catching it, and see, I'm predicting that it's going to fall. So that's what seems like they're doing. Oh, sure enough, there it goes. Okay, so you can see that I can trace that molecule and watch its path, how it was rising, rising, rising. And we could probably even go back to that moment when the red turns to blue and catch that. Aha, right there. So the red in my atmosphere window turns to blue. So kids can play with all kinds of things like this, where they are investigating and trying to figure out what's going on with these water droplets. So I'm gonna go back to my slides. And so what students have figured out here is that they are watching the simulation, and we've gathered some evidence from the simulation about how raindrops form, because that was our investigation question. What we did to figure out how raindrops form is we changed different variables. We observed processes and outcomes in the simulation. Oh, one thing I kind of forgot to show you when we actually go back to our simulation is that if I go back to run and I reset it, we can actually turn the wind on to the right. And then this starts to show us a little more of what might be happening on East Ferris Island. And what we figured out is that raindrops form when enough water vapor collects together, gets high enough, cold enough to condense into liquid water. And of course, I'm talking you through what we've figured out, but this is the work that students would be doing from talking to each other and observing and gathering evidence. There we go. We can see why more rain forms. But I'm going to go back to my slides again. So I press stop and coming back to slides. Okay, so here is all of this chapter that we're going through here, where we figured out about drops of water. We did some hands-on observations. We thought about how condensation from cooled water vapor is what happens when we're talking about when enough water vapor gets cold and condenses into liquid water. And that launched us into thinking about raindrops and how that connects. Oh wait, there's that same idea of it being cold, that we took on this other phenomena where raindrops form in the atmosphere. We gathered evidence from the sim, from the water encyclopedia again, that when water molecules get closer together, they form raindrops. When enough raindrops form, the rain falls. And then we're not getting into this last investigation question, but the water vapor gets into the atmosphere. How did it get there? We did trace that in our simulation. That happens through evaporation of surface water. Students figure out that by conducting a few more hands-on investigations. For example, having something wet in their classroom and seeing that it does evaporate. The water goes somewhere, and where does it go? They also read another book called Drinking Cleopatra's Tears, and this talks about the cycle of water, where it comes from, where it goes, after it leaves different parts of the water cycle. So what we're seeing here is a sequence of investigative phenomena. Like anchor phenomena, these investigative phenomena, or we might call them sub-phenomena, invite why and how questions. They lead students to investigations in which they discover important science ideas. An anchor phenomenon is selected or chosen for a unit because explaining it will lead students to discover a wide swath of other science content that a unit is meant to address. An investigative phenomenon is chosen because explaining it will lead students to discover something more narrow, one or two science principles. So an effective anchor phenomenon is specific, a pattern or event in a specific time and place. But an investigative phenomenon, on the other hand, may be specific, like a specific event that the students witness in a classroom, or it could be general, something students know happens in the world, and they figured out it must be happening, like raindrops forming up in the atmosphere. So investigative phenomenon are the stepping stones that help students eventually explain the anchor phenomena. So this is how it worked in one of the activities that we just explored. So one thing to notice is you can see that there is different kinds of investigative phenomena. The first one was something that actually happened in the classroom. The second one is a phenomenon students are likely to be familiar with, but it's not something we can directly observe. And so that's why it's a starting point that lets us get into the sim and read about it from secondhand sources, such as the Water Encyclopedia. So the scheme of phenomena-based teaching and learning is not new. It's something that we've seen in other countries or in other educational movements in like Finland and Scandinavia have used this type of learning for decades. The NGSS, we're so pleased to know, the NGSS features this approach and the ideas of anchoring phenomena, as well as the smaller pieces, the investigative phenomena. If you're using an NGSS aligned program, these elements should all be built into the curriculum. And so here I've just juxtaposed on this last slide here, again, going back to how we started, what's the difference between a phenomenon-based teaching and learning compared to topic-based teaching and learning? Our phenomenon-based approach, we can reflect on the differences. Students are engaged in figuring something out. They do that based on observable phenomena. In the case of how water drops form, it's focused on concrete, observable hands-on experiences. In the case of how raindrops form, it also provides something that students can observe, like a model, but it parallel processes to an everyday phenomenon. And then in that third one, where does water vapor and the air come from? They're both hands-on experiences where students observe at the macro level, meaning what's happening in the world around them, and then they engage with the sim to zoom in at the nano level, the microscopic level. And compare this to a topic-based. This is the one we're all familiar with and have likely either taught with or learned with in the past. What is the water cycle? Where students are asked what questions? What is evaporation? What is condensation? All right. So I want to thank you everyone for your participation in that. Hopefully you got some good insight and ideas into the difference between anchor phenomena, investigative phenomena, and what it can look like to guide students to figuring those out. I've got Heath back on the line. I'm going to go to my last slide, which is about your questions. And I do see we do have one question here I can go ahead and answer. One of our participants is asking, do the Amplify Science resources invite students to generate the questions? That's a really good question because I kept talking about the questions that guide the students. It certainly does. We certainly want to pose an interesting phenomena that students have lots of questions about and start to ask. That said, we know that we guide them towards certain questions that are posted and or narrowed in on by the teacher so that those become the questions that guide learning towards the standards we know that the grade level and the unit is meant to address. So it's a little bit of both. We do encourage lots of student questioning. We also start to narrow in on those questions to guide them towards where the learning goals are going in the unit. And then, yeah, Claire, just another response to not a question, but just to juxtapose again the difference between inquiry-based learning and phenomenon-based learning. And I think you hit it on the head when you just talk about how to organize a phenomenon-based unit and how to organize it is very different from the inquiry-based learning, which has that linear scientific method that many of us know and maybe loved from our own learning in school or perhaps the way we were trained as teachers. Phenomenon-based learning does require a different set of steps to help guide students towards figuring out. And that is all the questions I saw.
Yeah. Unless there are any more, going once, going twice. All right. Thank you, Rebecca. Very informative as always. I always learn something on these sessions as well. Thank you so much for everyone who took time out of your very busy days to join us for today's session. Like I mentioned when we started, you'll receive a link to the recording of this webinar in your inbox tomorrow to watch on demand or share with colleagues who may not have been able to join us today. Have a great rest of your day and thanks for joining.
Thanks, Eve. Bye, everyone.